Assalamualaikum and greetings everyone. Today my groupmates and I will be presenting our topic for CSC3003 project, which is graph coloring. Before that, I would like to introduce myself. I'm Sharifah Hana Masara binti Syed Omar and my metric number is 222635. So this is the table of content which shows all of the subtopics that we will be presenting today. So before we start, we would like to thank everyone who helped us complete this project from the bottom of our heart. Their cooperation and support have been invaluable to this entire journey. First and foremost, we want to express our sincere gratitude to Dr. Sharifah binti Muhammad Yassin, who serves as our lecturer, for all of her help, support, and advice. Her knowledge and perceptions have greatly improved the entirety of this project. We also appreciate the cooperation and teamwork of our friends for their commitment and diligence that have been vital to the accomplishment of this project. Lastly, we want to express our gratitude to whoever has contributed to this project directly and indirectly, which made this project much better. And we appreciate all of your help, inspiration, and efforts.
My name is Yuli. My metric number is 225789. I'm going to talk about what is graph coloring and the four color theory. What is graph coloring? In graph theory, graph coloring is a special case of graph labeling. It is an assignment of labels traditionally called colors to elements of a graph subject to certain constraints. In its simplest form, it is a way of coloring the vertices of a graph such that no two adjacent vertices are of the same color. This is called a vertex coloring. Similarly, an edge coloring assigns a color to each edge so that no two adjacent edges are of the same color, and a face coloring of a planar graph assigns a color to each face or range so that no two faces that share a boundary have the same color. The four-color theorem states that any map in a two-dimensional plane can be colored using at most four colors, in such a way that no two adjacent regions have the same color. This theorem, first conjectured in the 19th century, was proven in 1976 by Kenneth Appel and Wolfgang Haken using computer-assisted methods.
Hi, my name is Nur Fazana Ala binti Saharuddin. My metric number is 224263. So next we move on to the chromatic color and chromatic number. So what is the chromatic color? Chromatic color is a proper vertex coloring of a graph where no two adjacent vertices have the same color. Next, as for the chromatic number, the symbol, you can see there, the symbol, and it is the minimum colors needed to color a graph where no two adjacent vertices can have the same color. So we move on to the example 1. As you can see that in this graph, even though we use the orange color for 2 times, but the color is not used to color two adjacent vertices. So you can see that in this graph you have 3 colors, which are orange, blue, and green. So the minimum number of color is 3. Hence, the chromatic number also will be 3. Okay, next for the example 2, it is the same as the example 1. We can see that the same color is not used to color two adjacent vertices. And the color in this graph, we have 2 colors which are orange and green. So the minimum number of color will be 2. Hence, the chromatic number will also be 2. So next, we move on to the 4-color problem. So the 4-color problem is a problem in topology which is to figure out the minimum number required to color maps, where no two adjacent regions are the same color. Later on, was solved in 1977 by Kenneth Appel and Wolfgang Haken. So, the 4-color problem is examined in graph theory, where the vertex will represent the region on the map, and the edge, where they share 2 vertices, is where they shared border, and the graph under considerations are planar. We can see that as the picture shown besides, and no edges cross each other out. So how does the 4-color problem solve? It was solved by Kenneth Appel and Wolfgang Haken. The problem solved through computing and theoretical reasoning, where they created a catalog of 1936 unavoidable configuration, which were specific arrangement of regions in a map. So if any of the configuration exists or present in any graph, it indicated that the graph could not be four-colored. So if a map that is more than four-colored existed, it will lead into contradiction, which no such map exists. So conclusion, all maps are in fact four-colorable.
So this is the application of edge coloring. So edge coloring is a concept in graph theory where colors are assigned to the edges of a graph in such a way that no two adjacent edges share the same color. So the first application is the frequency assignment in wireless networks. So this figure shows the wireless networks, and this concept is applied to assign frequencies to communication links edges between transmitters, and the adjacent links do not use the same frequency. So for the reason, it minimizes interference and optimizes the use of available frequency spectrum. So the next application is the vehicle routing problems. So the figure below shows the example of a VRPTW with 3 routes and a single depot. So it is used in transportation and logistics, where the edge coloring concept can model conflicts between routes or paths taken by vehicles. So the benefits is that the coloring ensures that conflicting routes, such as those sharing common route segments, are assigned different colors, optimizing vehicle routing. So the last application is graph labeling in coding theory. So the table below shows the coding theory. So as you can see, the vertices represent code words. The edges represent the relationships between code words. The function encode information, and the benefit is that it can minimize errors during the data transmission.
Hi everyone, my name is Chuan Yi and my matrix number is 222333. So now, today I'd like to talk about the applications of graph coloring. So basically, what is graph coloring? So graph coloring is actually a method to solve complex and big problems. So each task or event were represented by a vertex, and the conflicts or dependency between the tasks were represented by edges. And there were no conflicting tasks have the same color, and it usually create an optimal schedule or timetable. So now I'll explain about the ways to apply graph coloring in scheduling. So in this question, they say that they have 12 faculty members in this mathematics department that had different sections, which is undergraduate education, graduate education, colloquium, library, staffing, and promotion. So there are 6 different sections. So we know from here that this different section that actually have the same committees. For example, undergraduate education, cinnamon, have the same committee with library also, which is cinnamon. Then limison and also limison in staffing. So in here, this way, I need to know that how do I actually manage the 3 time slot meeting so that the same committees can also join the meetings of different section, because they are not only the committees of one of the section. So this is why I've highlighted the same committees in different section with the same color. With, for example, cinnamon red, limison is orange, and so on. So after that, I will need to put it into a graph. So how do I know how to draw this graph is we need to determine the vertices, as I mentioned before, which is undergraduate education, graduate education, library, staffing, promotion, and colloquium. Then we need to know that the similarities so that we can draw the edges that connects between 2 vertices. So the vertices is represented by the section, so the edges are represented by the similarities between it, which is the same committees. So in these same committees is, for example, undergraduate education have the same committees with library. So I've connected undergraduate education with library. Then we have undergraduate education is also have the same committee with staffing. So I connected with staffing. Then we have also same committees with graduate education. So undergraduate education, we connect with graduate education. So this process move on until I have created this graph. So after I created this graph, I need to color it. So we noted that they cannot have the same color between two edges, between the edges that connected with two vertices. For example, if undergraduate education is yellow color, so I cannot connect it. They have the edges connected to graduate education, library, and staffing. So these three vertices cannot have the same color as undergraduate education. So this is why I color it as pink and also green. So first, okay, so I move one by one. After I color it as yellow, so graduate education cannot have the same color with yellow. So maybe I put it as pink. So we move on to library. So library have the edges with undergraduate, colloquium, and promotion. So for example, I have already yellow here. So I need to put it as pink because it does not connected with graduate education. So I can put it as pink. So next we move to staffing. So staffing, we connected to a graduate education, undergraduate education, and also colloquium. So actually, without noticing the color yet, I actually connected to yellow color and pink color. So what color you can choose? So I need to choose a different color besides pink and yellow. So that's why I put it as green color. Then the rest, I put this as yellow because it does not connected with the yellow color. So I can put this as yellow. So after I finishing the graph coloring, I need to separate it or aggregate it into different time slots. So first time slot, we have the same color is graduate education and library. Then second time slot, they have the same color is undergraduate education, colloquium, and promotion. And last time slot is staffing. So this is the solution for the first example. So next, I move to the next example for the application of graph coloring in exam scheduling. So in this scheduling means they have different courses. For example, course 1, course 2, course 3, course 4, until course 7. And these courses, although they have different courses, but they actually sometimes they take the similar subjects in it. For example, course 1 has a similar subject with course 2, and also course 5 because they take English, necessity of taking English, so they have the same subject, although they have different courses. So this is why we need to schedule an examination that does not clash with all these same subject for these different courses. So first we need to determine what is the vertices. So definitely the vertices is the courses C1 to C7. So that's why I created C1 to C7 here. After that, I've highlighted the similarities that represented the ages for different courses. So for example, maths is red, English is orange, and biology is green, and so on. So I connected the similarities between the ages. For example, C1 have from this graph, we know that C1 have the same course with C2, C3, C4, C5, and C6. So all this we have created into a graph that have the similarity ages and vertices. So after this, we need to move to the coloring section. Again, the same ages, they have the ages that connected to the different vertices, they cannot have the same color. So for example, yellow here, there's so C2 that connected with C1, C3, C4, C5, and C6 that connected to C1 cannot have the same color. So we have different color. And C7, I can have the same color with C1 because it is not connected to it. So this is why we have actually the minimum number of period is 6 because we have these 6 different colors, which is yellow, pink, green, purple, blue, and orange. After that, I can categorize it to different period. So for example, I know that I can have the same examination time for course 1, and course 7 because course 1 and course 7 they does not have the similar subject in it. However, we need to separate it from course 2, course 3, course 4, course 5, and course 6 because they have similar subject that clash with one another. So this is the solution of question 2. So next, I move to the third question, which is the scheduling and timetabling. So in here, we cannot have the we have the signals of 6 radio frequency station, and we cannot have the same interference or same channel because the signals does not interfere with one another. So this is when we move this table, the distance table, into a table that we know that the cannot interfere with one another. For example, station don't use the same channel with less than 150 distance is SB, SD, and SM. So this is the point that we take from it in order to know the connection between it. So this is when the time we start to draw the graph. as we know that SA have the similarities or have to connect the channel less than 150 miles means they has interfere with one another is SB, SD, and SF. So SA we connect with SB, SD, and SF. And continuously we do it and we have this graph come out. So after you have this graph, we start to color it again. So for example, SF is green color. We cannot we cannot have the same color with SF because it connect one another. So we can put this as red color. Then SP is also cannot have the same color with red color. So we put it as blue color. Then for here, we can put it as red color. Why? Because it does not connect to red color. However, he connect with blue color and green color. So this we also put as green color. Why? Because it does not have the same color with SA and SB also. And SD also does not have the same color with SC and SE, which is green, which is blue, and also red. So this is also the same method we're using it, but just we apply different type of color sequence only. So after that, that's our graph coloring. Then we need to categorize it into a conclusion. So in conclusion, that SA and SE can be together because they does not intersect one another and they have different colors. So it's SA and SE. And SB and SC, yeah, SB and SC has the same color and does not intersect with one another too. And lastly is SD and SF that have different the same color and does not intersect with one another too. So this is the conclusion for it. Then lastly, the question is about team building problem. So in this question is we need to divide, have 8 sets of students, and we need to divide into different groups so that they does not have the same friends or they does not have the friends that they know. So this is when we put it in the table first. For example, P, they have friends with QRV, Q have PRTU, and so on. So then we have those who have the same friend, we have connected it into a graph that have vertices and also edges. So vertices is the name of the friend, and edges is when we connect to the vertices that have the same friend, similar friend. For example, P have the friend with QRV, so P will connected to Q, P to connected with R, and P will connected to V, and moves and so on. Then we have created this graph. So after we created this graph, again, we will move to the coloring section. So the coloring section, again, that does not have the same color between the edges that connected to the vertices. So for example, W is purple color, so W cannot be, and U cannot have the same color, so they have different color, which is yellow and red. So P cannot have the same color with Q, R, and V, so that's why P is red. And Q cannot have the same color with P and R, which is red and yellow, so that's why it is purple. Move on and so on. So we will create this color graph. After that, we'll categorize it into 3 groups. Because we have used 3 color only, so we can categorize it as 3 groups. So in these 3 groups, we have know that red color, we have P and U that does not intersect to one another. And purple, we have QSV, which is also have the same color and does not intersect with one another. And we also have yellow color lastly, which has the same color and does not intersect with one another, which is R, T, and V. So you can notice that each color, they does not intersect with one another. That's why we have a different color. So that's all for the applications of graph coloring. Thank you for listening.
So for the conclusion of this project, graph coloring has a wide range of real-world uses and interesting theoretical applications. For example, applications in fields like complexity theory, information theory, and computer science. In addition to the classical problem categories, further restrictions can be placed on the graph, the color assignment process, or the color itself. Graph colorings can be applied to a wide range of everyday issues, such as reducing scheduling conflicts, and as of today, research on graph coloring is still ongoing. So that is all from me and my group mates. Thank you.